Hello learners, welcome back. Hope you had a good drink of water only so that you can get going with the valley climates again. And just to recap very quickly, I said anabatic, daytime, upslope. Katabatic, nighttime, downslope. And not downward winds, learners. We lose so many marks by saying downward. There's so many ways that air can move downward. It doesn't have to be anabatic or katabatic rather. It can just be downward winds. We must emphasize that. So let's look at what happens. Right, we just don't know that. We need to know why it moves upslope or downslope. So let's take the day. All right, the day that happens. What happens to the slopes? It gets warm due to insolation. That's the incoming sun's rays. Can you see it's coming through here and it's heating up the slope? Now, obviously, if the slope heats up, what's going to happen to the air above it? Obviously, it's going to heat up. And when air heats, what happens? It rises. Can you see the basic stuff again? Air rises. But note how the air is rising in anabatic. If I draw with your little pen, red pen that you guys like, the red one, can you see it's moving upslope? Upslope wind. Can you see the importance of remembering when air moves up the slope, not when air moves up? I'm going to scold you on that. Air moves up the slope is anabatic. All right? So let's go through it quickly. Slope warms due to insolation, right? What happens next? The slope heats up, the air above it heats up, and it moves upslope. Let's go to the nighttime. You can see the dark here. All right. Now what happens now? There is no insulation, so what's going to happen to the slope? During the night, when the slopes cool now, because the land is going to give off heat, and that giving off heat, that heat is known as terrestrial radiation. It's coming from the land. That is why it's terrestrial radiation. Now, obviously, as you're smart enough, you know this. If the land cools, what happens to the air above it? It's also going to cool. So if air cools, what's the basic principle? Cool air subsides. Okay? So the air then moves down. Am I correct? No. It moves down the slope. And that's why it's downslope winds. Are you getting that? Don't forget the word slope. Downslope winds. Okay. Learners, you got that. So upslope, anabatic, downslope, katabatic. I also do this in the class. I repeat it again. All right? Okay? So we can see here, terrestrial radiation. When it cools the slopes, the air above the slopes become cold, dense, and sinks down the valley slopes. All right? But there's also weather phenomenon more than the anabatic that's linked to the katabatic. Okay? It's associated with cold conditions, and frost can occur, especially in winter. Okay, I got winter here. All right, because what happens when the air comes down, and if dew point temperature is below freezing point, all right, and if this air reaches dew point temperature, it's going to form frost. Okay, thick frost. And I promise you, whoa, I lived in a valley as a young boy, and the frost used to be thick along that valley floor or slightly on the edges of the slope. Huge thick, because the dew point temperature was below freezing point, and when this air came down and the dew point temperature was reached, frost forms. So that's one of them at the bottom of the valley. All right, it damages crops, cold conditions. Right, and sometimes when there's condensation and not full frost formation, fog is created in the valley. Okay, and poor visibility can happen. Okay, in the area. All right, so that is about your anabatic and your katabatic winds. All right. So we look at this valley here. There's a river here. Can you see it? This is a valley. Okay. And I could ask questions. I could say, describe the wind that takes place, or state the wind that takes place in this area during the night. Can you see how you have to apply your knowledge? First I look at it and say, what wind? Oh, there's a river here, so it's a valley. So it's valley winds. Oh, during the night, it's coming down the slope. So therefore, it is katabatic winds. During the day, oh, it'll move up the slope. It's anabatic winds. Can you see it? I can do it on a topographic map, which makes it understandable also. So do not forget your topographic maps. Okay? Or your orthophoto also. All right. Let's go to another one. Thermal belts. Whoa. This is not a real belt. It's a heat belt. All right. That's where the word thermal comes from. But you don't use the word heat belt now. You say thermal belt. All right. Now let's take it. And there's a relationship between katabatic winds and the formation of a thermal belt. And can you see from this also, learners? Relate your concepts. Okay, relate your concepts. Now, if I look at this, I find the thermal belt is found towards the middle of the valley. All right, so what happens here? Let's take the night. Katabatic winds occur and air moves down the slopes. Now, because this is colder air, there is warmer air here. All right? Cooler air, colder air here. Please note there's no such thing as a massive difference. You may get it there at minus 5 or 2 degrees. Here it may be 3 degrees, but it's warmer air. So what does this katabatic wind do to the warmer air? It pushes it upwards. Can you see it? Now, it's night. It's colder. We also have air subsiding into the valley. Can you see why we need to say katabatic is downslope? Because this air is also moving down, and it is not katabatic winds. Because it's cold, air is subsiding greater. So we have this cold air that pushes the warm air up, and the cold air subsides into the valley. And what happens to this layer of warm air? It gets trapped between these two layers of colder air here. And that is your thermal belt. Let's look at the definition of it. A layer of warm air trapped between two layers of cold air. Okay, your thermal belt. There it is illustrated down here. All right. Now, it occurs during the nights, obviously, because that's when you have the subsiding air, katabatic winds, especially during a cold, calm winter's night. All right, I'm trying to be dramatic there. All right, cold, calm winter's night when air is subsiding and it's pushing the warmer air up. It's more pronounced. Again, can you see I'm using this? Due to terrestrial radiation, the upper slopes cool, it becomes dense and flows downslope, pushing the warm air up. Can you see it? I'm using katabatic winds. It's pushing it up. We have cold air above and cold air below, and the warm air in between. It's caught there. Now, what's so significant about the thermal belt? People build their houses there, halfway up the slopes, because it is warmer. Generally speaking, I know some of you love to freeze, but generally people like warmer area, all right, in the warmer thermal belt. Crops need warm, frost-free conditions will be planted in the thermal belt. Example, sugarcane. This is where we plant it. We won't plant it at the bottom if frost is going to damage those crops. So please note there is some form of inversion here, all right, where the colder air is below that. But remember, temperature inversion is basically as you go higher, the temperature increases. Don't just make that the definition of a thermal belt. Please, we find people mixing that up. A thermal belt straight is a layer of warm air caught or trapped between two layers of cold air as found in the definition. Although it may be related to temperature inversion, that the higher you're going, the warmer it's becoming. All right. Then we get the concept of frost pockets, okay, that form. Again, association with air moving downwards or downslope rather. Okay, so what is a frost pocket? A name for a low-lying area, example, a valley bottom, smaller hollow where frost occurs more frequently than the surrounding areas. All right, so why does it happen there? This is a normally dry, clear night, okay, when this can occur. So it's clear. Cold air drains down the slopes. Can you see it coming down? Katabatic winds. If the dew point temperature is below freezing point, it condenses to ice crystals. So the temperature must be below freezing point. And when the temperature is reached, you're going to get ice crystals. So you're going to get it from vapor to ice crystals, straight. All right. You know, it's a beautiful example of frost. Not exactly frost is when the gentleman that comes around selling ice cream in that little bicycle, and he's got a container, and then inside he opens it, it's got something known as dry ice. Frost is similar to that. Okay, don't put your hands on that, it'll burn you. Okay, so when it's below freezing point, condenses to form ice crystals, forming frost pockets where cold air collects. So wherever the cold air collects and it reaches the dew point temperature below freezing point, those are the areas where it's occurring. And that is why the word frost pockets are used. All right. Of course, it damages vegetation, natural vegetation and crops that are not resistant to frost. And the solution is you could plant frost-resistant crops. These are some of the things. But please, learners, whenever you write exams, etc., look at the context in which the resource is. And sometimes they give you a little extract or whatever. Then read there what is the things. And you find so many answers in those little descriptions. Okay. I'm doing really well in terms of my pen now. I'm impressed with myself. No backward, forward movements unnecessary. The last one on the weather conditions that we've been speaking about is radiation fog. All right? And remember, all these things deal with heating, cooling, movement of air from colder to warmer, higher to lower. Let's look at radiation fog, and this seems to be a challenge for many learners. This is too difficult. All right. It's actually quite simple. Again, it's cooling. Again, if you look at it, during the night. All right. The ground becomes cool during the night due to terrestrial radiation. So there's no insulation coming through. All right. Now the land gives off heat. And what that's known as terrestrial radiation. All right. The air above that land also cools. Okay. This air above here also cools as the cooling is happening. All right. Remember katabatic winds? But now it can be even a flat surface. When the air above is below dew point temperature, you know what happens at dew point temperature: condensation, generally cloud cover, etc. Okay, when the air above here is below dew point temperature, it causes the water vapor to condense around any dust formed there and other particles. Okay, so it creates like a thinner cloud near the surface, which creates this radiation fog. Can you see it here? All right, when it condenses due to reaching below dew point temperature, condenses and forms this fog, which is like a cloud near the surface. Radiation fog, because it's associated with terrestrial radiation being given off. That is why we call it radiation fog. Now, what happens in the morning? When the sun's rays hits the surface, there's the sun here now. All right, and it's shining and it's smiling. All right, this is the sun. Okay, and when it hits the surface, what happens? The surface heats up and the air above it also heats up. So what's happening? The fog is starting to dissipate, go down. And that is why we say the warm air rises and evaporates. It's like the fog lifts now. There's no fog here, it's higher up. Okay, generally this fog, if it exists, affects the visibility of people traveling through, etc. So when they say radiation fog, you tell your parents, just watch out, this can happen. You understand? Don't tell them about dew point temperature, etc. Just tell them about the danger about visibility. Just kidding, learners. All right. So that is your valley climate. So can you see there's not much. Together what Mr. Nate taught you about tropical and middle latitude cyclones, the section is not difficult, learners. All right. Let's go to the last piece. Urban climates. And we notice already when we look at heat island, we're going to define it. We're going to look at the effects of urban heat islands. We're going to look at strategies to reduce heat islands. Then we're going to look at a concept known as pollution domes, because learners mix up, and we find this in many situations. And I know Miss January is shaking her head there also. You mix up the concept of urban heat island and pollution domes. So we're going to try and differentiate here, and we're going to link them. Okay, we're going to look at the definition, the effects and causes of that, and strategies to reduce. And this is the last piece of climate and weather. Okay? Now, first thing, the main emphasis is on the urban heat island. We need to look at what is the urban heat island. All right? How do we define it? All right? Remember the word urban here. So we say it's an urban area of higher temperatures surrounded by a rural area of lower temperatures. If I say it's an area of higher temperature surrounded by an area of lower temperature, then I'm just defining an heat island. It's urban heat island. So I have to talk about the urban area of highest temperatures surrounded by the rural area of lower temperatures. Again, I'm emphasizing the point, learners. It's 2 marks for definitions. So if we're not going to answer it fully, we're losing 2 full marks. Okay, so let's start looking at now, why is the urban area having a higher temperature than the rural area? Okay. Let's just take it just to 2 pictures first. Okay, of course, you know, this is your rural and this is your urban. Before we even look at the concepts more specifically and the reasons, all right, we can look at here. Open water surfaces. Open surfaces with vegetation, so there's more absorption. Trees absorbing heat. You understand? All these factors cooling the rural area. Let's look at the picture of this, all right? We notice building density. Can you see it? High buildings, close together. Okay, winds can't move easily to cool the area. Concrete, steel, and tar. All right, all this is here which absorb heat. And you can see many cars. I'm not seeing it clearly there, but there's a lot of cars there, a lot of people, a lot of activity. All right, so a lot of heat generated. So by just looking at these 2 pictures, you clearly see that there is a significant difference in terms of the infrastructure and the activities that would actually cause a difference in the temperature, meaning that your urban area has a higher temperature than your rural area. Okay? Now, let's go on. Reasons and causes, as I highlighted in that. Let's look at it. Human activities in urban areas contribute greatly to the difference between rural and urban climates. You know, there's businesses, there's furnaces working in the factories, and you find this all in the urban areas. Air conditioners also. I know you may say air conditioners are cool, but if you go on the outside of the building, it's giving off the heat. People in there, busy working, etc. Machines working. So a lot of human activities contribute to this. And they alter the climate, the local climate, through industries. Industries are one of the biggest things that give off a lot of heat in the urban areas. Higher temperatures due to artificial surfaces found in the urban areas. And again, I'm emphasizing it, concrete, steel, I think I like the word concrete, I said it twice there, tar, absorb more heat, okay? All these artificial surfaces absorb more heat. You know, on a hot day, learners, if it's 40 degrees and you take off your shoe and you walk on that tar, I don't want you to do that. It's hot. You can even fry an egg on it. All right, so it absorbs a lot of heat. And in the rural areas, how much do you see about that? You don't see freeways going into the farmer's plot. He doesn't need a freeway. He may just need a simple road to take you there. All right? So you don't get such huge buildings, etc. Okay, farmers don't live in the skyscrapers in the rural areas. They're more active. They're on the land, farming, etc. Okay, so more activities in the urban area, more fuel combustion. As you're driving those cars, those combustion and the exhaust fumes that are coming out, making it hotter, businesses, air conditioners, okay, make the urban area warmer. Now, there's more cloud cover, fog, and precipitation in the urban area. Okay, right. This seems to be a bit confusing, isn't it, learners? We picked up the point that the urban area is more concrete. There's more open water surfaces in the rural area. They should have more rainfall. Now, what actually happens here, learners, I'm going to draw a little sketch here. And I'm going to say that is rural. I'm so impressed with my writing. It's not even jumping. I think I'm scared of you, learners. All right, that's the rural area. And this is the urban area here. Okay, what did we learn? The urban area is warmer. Okay, so if the urban area is warmer, in relation to the rural area, it's going to have a lower pressure, isn't it? And if the rural area is colder, it's going to have a higher pressure. Higher pressure. Can you see? I'm going to draw my HPs. I'm so impressed with my writing. I'm going to make sure I write HP everywhere. It looks so nice. Okay, learners. So there's a higher pressure in the rural areas. Okay. So although the rural areas may have more humidity, more water surfaces, now what's going to happen? Air is going to move from that high pressure to the low pressure. Can you see it? And what is this air bringing with it? Moisture. So that's where that humidity comes into the urban area. And you know that the urban area has more dust particles. Okay, it's warmer. So what happens to this air when it reaches the urban area? It heats up and rises. And as it rises, there's more dust particles, which means there's more condensation nuclei, and the water vapor condenses on them, forming more droplets of water, more cloud cover, and more rainfall. And that is why your urban area gets more rainfall than your rural area, although the rural area has more water surfaces. So in the short here, it says more precipitation due to more condensation nuclei and moisture that comes from the rural areas and moves there. Okay. Also, another factor that could actually affect is the slower wind speeds due to friction from tall buildings found in the urban areas. And I'm going to draw some tall buildings here. I'm so impressed with my drawings now. I'm going to draw more for you. Okay. Now what happens? As the air hits the tall buildings, there's friction. It slows down the movement of the wind. And you know, when winds move at a faster speed, it cools down the area. You know, when you put the fan on, and I suppose in your houses, you got air conditioners. I'm a poor guy, I got a fan. When I put it on, it actually cools because there's more wind, and I put it at a higher speed, it cools further. So by slowing the movement of those winds due to the buildings, it doesn't allow for more cooling, so hotter. But in the rural area, where we've got those little trees and not much tall structures, the wind flows freely and therefore resulting in a cooler area. All right. And now, learners, as I said, I've learned such a technique that I am going to erase all here, okay, to show you a few more sketches of this. All right. So I'm going to do that, and I'm going to ink again. So we picked up that the slower wind speeds due to friction and more tall buildings. All right. Now, the low relative humidity due to less vegetation and urban drainage systems. Okay. So in the urban area, those stormwater pipes are massive. You know the best way I can describe this? I watched a little movie when I was younger, the Ninja Turtles, I think it was, and they lived in these big pipes in New York. Those are stormwater pipes. So in order for this urban area not to actually get flooded, these stormwater pipes take it away. Now, because there's less humidity and less vegetation, less heat is absorbed. Okay, and that also results in your urban area being warmer. Remember, vegetation absorbs heat for photosynthesis, etc. All right, and if there's more humidity, it absorbs heat. Okay, so it makes the urban area warmer. And then there's multiple reflections, and people tend to be a little bit confused. And that is why I cleaned my little screen here so I can show you. Right. Now imagine the heat being trapped by the glass here in these buildings. It's then reflected sometimes onto this building, and then it gets absorbed there, and then it's reflected here, it gets absorbed there, and then it gets reflected there, it gets absorbed there. And what's happening? The heat is now being trapped between the buildings in the urban area. Okay, do we get this in the rural area? We got our little trees again, and our vegetation, and the wind moves more freely, and therefore not trapped by multiple reflections. All right, we spoke about the stormwater pipes and also a large amount of people, huge amount of people that's found in the urban areas. All right, that's also giving off heat. We're not going to describe how they gave off heat, but they're giving off heat a lot of times. All right, and moving around, working, etc. That makes the urban area warmer than the rural area. Okay, learners, now, the effects of heat islands, I think you had that in your prelim paper also, eh? Because of this extra heat in there, we get heat-related illnesses and fatalities due to incidents of thermal discomfort when it's too hot. We have cardiovascular illnesses, respiratory problems. When it's too hot, people can't breathe, especially people at my age. All right, you may be a little better. Okay, so heat strokes, heat exhaustion where people faint due to this. Increased pollution results in respiratory problems also, because now this air is moving up with all the pollution. Smog reduces visibility, okay? High temperatures may produce physiological disturbances in plants. You know, people talk to plants also, eh? So they also have this change due to higher temperatures. They may die out, they may change in terms of the physiological structure because they're not used to the heat. So even plants struggle, animals struggle, you understand, because of the change in the heat. So it's not only an effect, a human impact, but it's a natural environmental impact also that happens down here. Okay. And then the pollution dome. Now, we find this in many cases, and my colleagues tell me learners mix this up with the urban heat island. All right? Now, the pollution dome is a layer of pollution found above an urban area. Now, please note, this is the causes of this little thing down here, okay? Contributing factors are human activities, industries, vehicles. They all give off pollution, all right? Or carbon dioxide, etc. Okay. The stable air over the urban area traps it. Okay. So visualize this. There is your urban area with your buildings and your cars and whatever. And remember, from the top, there is subsiding air. Okay? So this pollution goes up until it reaches the subsiding air, and the subsiding air then traps the pollution. All right? Now, we'll notice something here. If I created this, all right, and I'm going to make some big lines across the words here. This is the night. Can you see it? And during the night, when the pollution is given off, because of a great amount of subsiding air, can you see we're using that subsiding air again? Because there's a great amount of subsiding air, the pollution dome will lie closer to the city and its buildings because of the large amount of subsiding air. During the day, it's hotter, there's more heating of the surface, etc. There's more rising air and less subsiding air. Can you see that? Okay, less subsiding air. Now what happens? The pollution dome is more, because the air is heated and more spread out, the pollution dome is more anvil shape and higher up, due to less subsiding air and more heated air that's coming from the interior or from the urban area itself, and it's spreading out. Can you see it? So, let's look at this. Pollution dome is higher during the day and lower and more concentrated during the night, because during the night there is more subsiding air. Okay? And that's what happens there. Now, the effects of pollution domes. What does it do? It contributes to the formation of heat islands. And that is the most significant point here, learners. It's not the heat island, but it contributes. Now imagine this pollution dome hanging here. Wouldn't it trap heat in this area? Can you see it? Heat will also be trapped. And it will add to the effect of the heat island by making it hotter. The thicker the pollution dome, it will add to the increase in the temperature by trapping the heat. That is the relationship between an pollution dome and the urban heat island. Obviously, if you get rainfall, etc., with all the pollution, you'll have respiratory problems, more pollutants, more condensation nuclei, more precipitation. All right? Okay. And you get fumes that are trapped, but are given off by cars, lead poisoning, petrol fumes. And when it rains, it comes down as acid rain, which can damage the health of the people. Now, there's been a few requests, learners, regarding the calculations and regarding one or two aspects of the cyclones, etc. But before I go forward, I'm going to ask my colleagues if there's any area of concern that has been mentioned to them before I go forward. All right. I have done these calculations before, but there has been a request on these issues. Okay, so I'm going to very quickly there was an area that picked up in terms of your mid-latitude cyclones, and I'm going to very quickly go to that. Okay, now learners have asked about the jet streams. Okay, now generally we talk about an obstruction. Yes, there can be a obstruction, all right, that would cause a wave in the mid-latitude cyclone. But I want to just talk about the jet streams, which play a very big part in the formation of mid-latitude cyclones. I'm now sorry, learners, that I'm jumping from here to there to there, just to highlight certain of the areas that you were concerned about. Now, jet streams are currents that are found high above the earth, okay, and they move easterly at altitudes of 8 to 16 kilometers. So if you have your front and they blow, all right, at heights, what's going to happen to the front? It's going to curve. So that's your jet streams that will form. Okay, another one that learners were picking on, and of course, if you have further things, you can then ask for comprehensive notes on that, is the formation of cumulonimbus clouds. This is the cold front, by the way, and this is the warm front. All right, now the formation of cumulonimbus clouds here and cirrostratus, etc. here. Big thing to note, this is a cold front. The pressure gradient is steep, and this is the warm air in front of it. So I would always describe it like a sumo wrestler coming towards a jockey. All right, the sumo wrestler is heavier, the jockey is lighter, he's going to push him right up. All right, I hope I didn't offend any sumo wrestler or jockey. But what happens here is this cold, heavy, dense air comes in and wedges underneath the warm air. Okay, and there's a rapid upliftment of the warm air. And that is why we talk about the vertical extent of a cumulonimbus clouds. Can you see it? Because it's such rapid upliftment that it shoots it right up. And as it's going up, it's cooling and condensing. And that is why you got this cloud of vertical extent. Here the air is warmer, so the warm air rises along the warm front. It's like overrides it. Okay, so it rises along the warm front, and therefore you can see it's more lateral, all right, in terms of its formation. That's the question you also asked there. Then, another one you looked at. Now, I'm just going to go to the basics here, learners. Occlusions. I'm going to draw one here. Okay, and I'm going to draw one here. And then I'm going to put the cold front here and the warm front there. And then I'm going to put cold, warm, cold. And I'm going to put the cold front here and the warm front here. And I'm going to put cold, I'm going to put a warm, a cold, and a warm. Okay, now, if we look at this, that's touching in here. I'm going to call it touching, so simpler to understand. All right, you see that's the cold front. And when you notice this, if it's a cross section, it's a cold front occlusion. All right? Yeah, you see this is the warm front. And it's touching in there, that's a warm front occlusion. Can you see that? Also your last symbols, where the occlusion has occurred, if your last symbol is a cold front symbol, cold front occlusion. And if your last symbol is a warm front symbol, it's a warm front occlusion. I'm just giving the basics that those people, those learners who have the potential but are finding challenges with this section, you can use simple things here. All right, and you notice with the cold front occlusion, what happens here is the cold air undercuts the warm air. And here you will find that there's overriding of the cold air above the warm front. Okay, so that was something that you seem to have a challenge with. These things, but of course, I'm just going to them quickly so that the areas that we look at. And here, the only area of concern that seems to come up is that sometimes, how do we look at in terms of defining or identifying the stage? Because in the immature formative stage, immature stage, you would find that the temperature is below 992. And sometimes in the dissipating stage, the temperature is around 992 also. Remember I told you about the synoptic map? If there is land and if the cyclone is moving over land, you would find that it's dissipating, even if the temperature is 992. Secondly, you will notice the dissipation of the forward left-hand quadrant as shown here compared to here. All right? Can you see that? Okay. These notes will be available. Then here we spoke about the eye, all right, and the eye wall. The eye wall is also known as the quadrants. Okay, this is where the warm air comes up, rises, okay, and as it rises, there's rapid upliftment in this eye wall, which is the quadrant. Due to rapid upliftment and cooling, cumulonimbus clouds form, okay, along this eye wall, and then that way it forms that, and that is where you have your heavy rainfall, okay? Now, in the eye, air also rises, but there's subsiding air also that comes back into the eye. And the eye stays calm, and there's clear skies, because the subsiding air heats up, you understand, and doesn't allow for more condensation and cloud cover. So that is why you have your clear conditions, okay, in this aspect here, okay. Then it seems again there's a challenge when it comes to our little vertical exaggeration. Now, I want to get clear with you. Again, we did it in the first show, okay? And this can come out in any paper. It can come out in paper 1 or paper 2. And you'll notice there's a change in the way marks are allocated. And learners, you can score marks here. All right. Now, if you looked at the vertical scale, it says 1 centimeter represents 20 meters. Okay. This scale of the cross-section can be the topographic map or the orthophoto, which you need to be careful about. All right. So here, you need to look at which map are you using. Is it a topographic map? The scale will be 1:50,000. And if it's the orthophoto map, it's 1:10,000. All right? 1:10,000. So there's difference. In this case, it's a topographic map. So just to get clarity, this is not a ratio scale because it's centimeter and meter. You need to change it to a ratio scale. All right? So how do we do it? We have to make both units the same. So this is 1 centimeter. I have to take the 20 meters and make it to centimeters. So how do I make the 20 meters to centimeters? I take the 20 and multiply it by 1,000. And that's when I got my 2,000 centimeters. Now, as soon as I work out the 2,000 centimeters, I'm getting a tick, learners. I'm actually getting a full tick. Okay, now I need to express it as a ratio scale. Okay, as soon as I write and I make sure I highlight that is the vertical scale. And I show vertical scale and I write 1:2,000, I'm getting a mark for it. So already 2 marks just for the vertical scale, conversion, and then showing it as a ratio scale. And then when I write horizontal scale, I get another mark for it. Exactly. So I take it from the map and I write it. Now just work this out, learners. I've already scored 3 out of 6. Can you see that? Okay, so I don't know why there's a concern about it, but I'm doing it again today to clear it. Maybe the last time we went a little bit faster. So then, now what does the formula indicate? It says vertical scale over horizontal scale. And if I substitute correctly, I'm just going to get the mark. So I know what's my vertical scale, I know what's my horizontal scale. I can either put it as a fraction, vertical scale over horizontal scale, or I can put it as a ratio, 1:2,000 over 1:50,000. I've got a mark already. Now what have I got? Sorry, this is out of 5. I've got 4 out of 5. Without even working out the answer, I've scored 80% already. And of course, after I work it out, remember I have to invert and multiply in order to work that out. And then it goes 1, 2, 3, 1, 2, 3. 250 divided by 2 is 25 times. And that gives me my 5th mark. And let's say sometimes there's a calculation error. You just miscalculated. You still score 4 out of 5. And that is important, learners, in terms of scoring marks. Make sure you show your steps. All right. And then there is one more that seems to create a challenge. And that is your gradient. And I know Mr. Nair has picked up on the magnetic bearing, but it seems to be a challenge again. But let's go through the gradient one first. Now, notice, learners, that there's the word average gradient here. This is not the exact gradient between the two. It could go like this. Okay, because it's points that rise up. So, also gradient is relative. We can't say what is very steep, what is very gentle. But let's just look at the calculation again. What is vertical interval? Simply it means difference in height. And I'm sure all of you can work it out, learners. This is a trigonometrical station. That's the number and that is the height. 1233.5. This is a spot height, 1256. All I do is I measure a -1 from the other to find the difference in height. 1256 is bigger, so a -1233.5, and I got an answer of 225. Already I scored a mark. Can you see it? It's just the difference in height. What is the horizontal equivalent? All right, we don't know why, learners, and just learn it like this so it makes it easier. Is the actual distance between the points. Okay, the actual distance. So my first thing is I have to take it from the dot to the apex, take my ruler and measure it, and I get 5 centimeters. Can you see my 5 here? As soon as I measured it, but please note, I must write VI for the 225 and I must write HE, because if you don't write that, you don't know where it's actually fitting in and you don't get the marks for it. So immediately, as soon as I measure that and write 5, I already got a mark. That's 2 out of 5 marks. Can you see it? Don't just focus, don't stress. Am I going to get the answer right? You understand? No matter how I try and mess up the answer, look at how many marks you can score in the steps. Okay, now I know if it's simply because the bottom answer is going to be, or the top answer is in meters. Can you see it? I must also make the bottom answer in meters so it's easier to calculate. So if it's the topographic map, I'm using 500. If it's the auto map, I'm going to use 100. Be careful which map you are looking at. All right? Be careful so that you know exactly, because sometimes we find learners, when we mark scripts, we find learners, because they don't focus on which maps they use the wrong scale. They use 500 instead of 100. So if I multiply it by 500, can you see that, learners? And I work out the answer, I've got that. So by just working out my VI and my HE, I already scored 3 out of 5. Can you see that? Already 3 marks out of 5 marks. Now, for substitution. Even if the VI and HE is wrong, if I substitute correctly, I would then look at this. That's my VI. It goes on top according to my formula. That's my HE. It goes below due to my formula. All right? So, when I look at this and if I substitute correctly, I got a mark. Without getting my final answer, learners, without getting my final answer, I've already got 4 out of 5. Those great mathematicians, I know you just say, man, I can get the answer like that. Different things. Try to follow the common method. All right, try to show all the steps, even when you get to this. Try to keep it to 2 decimal points at the end, okay, so that you are clear with all that. This interpretation of this, all right, this is 1, and let's say that is 10. This is 1, and I'm going to go right across, and that's 1 is the vertical, horizontal is 111. So the bigger the number here, the gentler the gradient. You have to compare gradient. Which one is more gentle, which one is more steeper? Because gradient is relative in terms of your answers. Learners, I think my time is coming very, very close. You understand, to finishing. I wish I could have another 2 hours because I know you sitting there very, very enthusiastically. And of course, I'd like to once again thank the Gauteng Education Department for their support in these programs, to my colleague, Ms. January, who has been busy looking at all the different things and trying to help you with additional notes and video links for further lessons. And if you require it further, we'll be here for a few minutes to assist you with that. I'd like to thank the team here who have supported me, and especially with my lack of technology and that. And the learners, remember, geography is about application. Do not forget your past papers. Make sure each time you do an activity, do it. So, thank you for watching this lesson. Please remember, sanitize, wear a mask, maintain social distancing, and looking forward to seeing you again. Goodbye, learners. All the best.